Lesson 8.6, Modeling Problems Solving with Growth and Decay. So now we're going to take everything we've done so far and now apply it to word problems. Our objective today is to write and evaluate exponential equations in context of a situation. We're going to basically be writing an exponential equation and then using it to evaluate something. We also will look at some linear models as well today. First up, though, vocabulary. So exponential growth and decay. We're going to be using a very unique formula because we got to look at finding what that rate is now this time. So this is the formula we're going to use. It's very similar to our y equals a times b to the x power. Okay? But we're going to have this 1 plus or minus r to help know if we're going to be growing or decaying. So first off, the a value is still our start value. So it still goes in front, still our y-intercept. The plus or minus indicates it's whether growth or decay. Growth, positive, decay, minus. Makes sense. R value is our rate, which we need to make sure it's in decimal form. And then the x value will, of course, be like the time. Years, days, months, whatever they give us. What you want to make sure is that we only use the exponential growth and decay formula when we're looking at rates with a percentage sign. It will say by 12% or 2% or 5.6%. That's when you use the exponential growth decay model. The other is linear growth and decay. That is, of course, just our good old slope-intercept form. We've seen it before, we'll see it again. M is our rate. So if it's growth, we add it. If it's decay, we minus it. And then, of course, B is our starting value or our y-intercept. This is only used when you are adding or subtracting by a value. So like it increases by 2,000 or decreases by 5. That is linear. If it has a percentage, exponential. Speaking of those two, when it is a growth model, this is what's going to happen to the equation. We're going to add r for exponential, and we're going to add to m for linear. When it's decay, we now subtract r for exponential, and then we subtract m for linear. Okay? And just remember, rate for the exponential needs to be written as a decimal. Okay? 5.5% is not a decimal. It's still a percentage. So divide it by 100 to get that decimal. First one up. Examples. Calculating exponential growth / decay. So we're going to go ahead and again, I would have a highlighter ready because as we read through it, we want to highlight stuff so we can get the good information out. The San Francisco Zoo did an experiment testing rabbit population. Okay, so we're talking about rabbit population growth. They started, ooh, I like that word, started with a group of 15 rabbits. That must be our starting value. They discovered each year the population grew by 25% a year if unchecked. What would be the rabbit population? So we got to find the rabbit population. B, if the rabbits were left to populate unchecked for 10 years. That must be our time or our x value. So we're going to need to first write this formula out. Since it is increasing by a percentage here, that means it's exponential, which means we need to use the exponential form, which is y equals a times the quantity of 1 plus or minus r to the x power. We're going to go ahead and now calculate or find our values of a, r, and of course x. So a again is our starting value, and we are starting out with 15 rabbits as they stated. So that'll be 15. Our rate is our percentage, which is 25%, but we need to make that a decimal, so we're going to divide it by 100, which gives us to be 0.25. And then x is our time, which is, of course, 10 years. We're going to go ahead and plug this in. Y equals 15, 1, and then do we add or subtract here? Because we got to worry about that plus or minus. It did say we grew, which means it's growth, which means we add. 0.25 for our r, and we're going to raise that to the 10th power. We can rewrite this as y equals 15, 1.25, because we can simplify the inside to the 10th power. So let's see, how many rabbits will there be after 10 years? So we're going to go ahead and get our calculator out and plug this in. 15, and I would be doing this with me if I were you. 1.25 raised to the 10th power and we get 139.6983826. Well, let's talk about rounding. Well, can you have a whole rabbit or can you have a half a rabbit, really? No, you can't. It's either we have a whole rabbit or not. So we're going to round to the nearest whole rabbit, which means the nearest whole number, which is the ones place. So 139.6 will make that 9, or really the 39, round up to 140 rabbits. It's rabbit season. Now, you could also have put this part in the equation too as well. It will still populate the same value. So what will the rabbit population be after 10 years? 140 rabbits. Awesome possum. Let's go again. So here we have number 2. Overcrowding is a big issue in India, which is the largest population density in the entire world. There are so much people cramped into one little town, resulting in not enough water and food to go around. A town in India is estimated to be able to handle 95,000 people. That's their capacity. And notice I'm not highlighting it because it's not a starting value. Currently, a town has 75,000 people. There's our starting value. And it's growing, so we're going to be adding again, at a rate of 12% annually. Will the town be over capacity by the 5th year? Well, we need to find out, well, how many people are going to be in the 5th year to even see if it's over capacity, which means over the 95,000 people. So again, since this does have a percentage in the problem, we are looking at something that's exponential. So we're going to use that exponential form of y equals a times the quantity of 1 plus or minus r to the x power. Go ahead and find your a, your r, and of course your x. A starting value, 75,000. R, the percentage as a decimal, so let's divide it by 100, which gives us 0.12. And then x, our time in years, which we're looking at after 5 years. Go ahead and plug this all in. 1, and then, oh, is it adding or subtracting this time again? Well, we are growing, which means we're going to add that r value as a decimal, which is 0.12, and raise this to the 5th year. So again, you could put this exactly in a calculator like this, or you could simplify it by combining the inside, which will make the inside actually 1.12 to the 5th power. It's up to you, whatever is easier for you. So I'm going to show you how you can do it the other way. I'm going to do it one more time, and after this, I am not showing the calculator work. So I'm hoping you are working this with me as I am. So I'm going to put the top one, 1 plus 0.12, and raise that to the 5th power. If you want to, oops, that's not raised. If you want to do the other one and see if it's the same, by all means do so, because I'm pretty sure it is. Now we're talking about people here, so this value is representing people. Can we have half a person? No. Short people are considered a whole person, so get that to your head. So we're going to round this up to the nearest person, so it won't be 75, it'll be 76 there. So it'll be 132,176. 132,000, and then what was the rest? 176 people. Now that's not our answer. Our answer had to be, will the town be over capacity by the 5th year? Well, if this is capacity, 95,000 people, is this over it? Yeah, it is. So will the town be over capacity? Yes. The town will be over capacity. Which means that some people are not going to get enough food to survive, so they're going to have to go somewhere else. It stinks, especially if they lived in that town for a long time. All right, number 3. This one is for you to do, okay? It's very similar to the last two, so go ahead, pause this video, and try this one out, please. Pause. So here we had Eddie that made an initial investment of $4,500 into an account earning 5.15% interest annually. How much would Eddie have by year 6? So after getting our values, converting our percentage to a decimal, which again indicated that it was exponential, we plugged it all in, simplified it a little bit, and then calculated that Eddie would have $6,082.30. Again, we did the adding here for our formula because we were earning money, not losing it. I got the hiccups for some reason. Whew. All right, number 4. Guess what? I want you to pause this video and try this one out, please. Again, it's very similar to the other ones before it. Pause the video. So, this one involved our immune system. Bob was exposed to a bacteria that was causing him to have strep throat. They told us that the initial bacteria count was 65,000. We are trying to destroy those bacteria at a rate of 10.5% per day using an antibiotic. And we want to know how much does he have left after 3 days. So, well, we plugged our values. And this time, though, that plus or minus happened to be a minus sign. And that's because we are destroying things. So we're losing them. Okay? So our end result should be smaller than what we started with since we're trying to get rid of this bacteria, which it was, and it's 46,600 bacteria cells left. Remember, you need a round to the nearest bacteria cell, so be careful when rounding. All right, now we're into the comparing problems. We're going to look at something exponential versus something that's linear. Okay, so here's our first one. In nature, if one particular animal population gets too high or too low, another animal population will suffer. In the plains of New Zealand, geckos hunt insects like cockroaches. If the gecko population gets too high, it may cause cockroaches to be wiped out. It is estimated that and here's our first thing we're talking about, gecko population, which is currently 2,000 starting value, is increased by 10% annually, while the cockroach population, our other people, currently at 300,000, is increasing by 20,000 annually. They want to know, will the gecko population overtake the cockroach population in year 15 or in 15 years? So this one actually requires you to write 2 formulas, which is why we discussed earlier today our linear and exponential growth and decay model. So we're going to use these 2 models depending on what, of course, the information is. Is it exponential information or is it linear information? How do we know that? Again, is by if there's a percentage or not. So the gecko population, which I'll do in blue, was increased by 10%. That 10% means it is exponential. So let's do that one first using the exponential form, which if you're not writing it down as much as I have, yeah, better, because you got to know this one, kids. This one I can't give you. So again, find those values to plug in. A, our starting amount was 2,000. R is 10%, but we need it as a decimal, so divide it by 100 and get 0.10. And then X, of course, is the 15 years that they're both going to share. So let's go ahead and plug all that in and find out what it equates to. So 2,000, parentheses, 1, and are we adding or subtracting here? Well, we're adding because we're increasing. So plus 0.10 raised to the 15th power. Go ahead and get your calculator out and evaluate that, or just simply wait for me because you don't want to put this thing out, which is fine because when it comes test time, you're going to struggle and I am just going to laugh on the inside. So we have, and we're talking about population of geckos, so we can't have half a gecko, even though geckos can have their tail removed and still run around. So we're going to go for full gecko here, and it looks like it will be 8,354 geckos. So now we need to do the same thing, though, but for cockroaches, which we'll do in green. Now, for cockroaches, they gave us some different information. First off, we're currently at 300,000, and we're increasing by 20,000 annually. So this increase of 20,000 is our rate of change, and it's a value, which means this one is linear. Percentage, exponential. Value, linear. So what is that rate of change? What are we increasing by? 20,000. So we're going to add 20,000 for that M value. It's going to be a positive, basically. Then, of course, what are we starting out at? That was the 300,000, which is our B value. Then, of course, what's our x value? Well, this, of course, our years, and that is being shared, which is 15 years. Let's go ahead and plug our values in. So it'll be 20,000 times 15 plus 300,000. Let's go ahead and find out how many cockroaches will there be. So go ahead and use your calculator, evaluate this out, and I would make sure to at least know how to put this in and make sure that you're putting in correctly, because you would hate to get the wrong answer on test day, which is Friday. We get 600,000 cockroaches. So they want to know, will the gecko population overtake the cockroach population? Well, do we have more geckos than cockroaches? Nope, and not even coming close. So, of course, this answer will be no. The gecko population will not overtake the cockroach population in 15 years. Let's go ahead and write that out, and I'm going to type it out to make it a little bit easier. So we're going to say, no, the gecko population will not overtake the cockroach population. And I can't spell population, so we're going to do this because that is how we spell these days. All right, your first one done. Let's do one more together, and then I need you to try the rest out. So let's look at one more here. You are offered 2 jobs. Job A gives you a raise of 5 Ooh, I need to get my highlighter out. This is some good information. Job A gives you a raise. Raise means I increase by 5.6% each year, while job B gives you a raise of $2,000 a year. 2,000 linear, 5.6% exponential, so it's a percentage. They do tell us that each job starts at $57,000. So if you're planning to stay there for 8 years, which job would you choose? Because you want the one that earns the most money. And then, of course, explain why. So let's go ahead and, again, look at the values to find out which one's linear and which one's exponential. So if I look at my first one, it's a raise of 5.6%, job A. So since it is percentage, that makes it a exponential function. So then we write the exponential form that we will be using to evaluate it. A value is, of course, our starting value, which they both start at 57,000. Oh, that does not look like a 5. We need to fix that. My R value is my rate, but as a decimal. So we're going to take that percentage, divide it by 100, and we get 0.056. And then, of course, our X is our time, which is 8 years. So let's go ahead and find out from job A, how much money will we have after 8 years? Let's go ahead and plug everything in. And then, of course, add or subtract. I don't know. What are we going to do? Add or subtract. Are we earning or losing money? Raising money. That means we're definitely earning more. So we're going to put a plus sign for that guy. And then, of course, finish it off. Our rate is 0.056. And we're raising this to the 8th power. So go ahead, do your calculator work. 57000. 1 plus 0.056. Raise it to the 8th power. We get, are we talking about money? Yeah, we are. So it would be $88,142.67. We're rounding to the nearest cent because literally in a job, every cent counts. All right, now let's look at job B. So job B was increasing by a raise of $2,000 a year. That's just the value, which means that is just linear. So write down the linear equation and then find your variables, M, X, and B. M is your rate of change, which we're increasing by $2,000 a year. So we're going to add it. Our starting point was the 57,000 that they both started at. And then the X is the same thing. We're looking at both after 8 years. Go ahead and plug this in. We're going to have 2,000 times 8 plus 57,000. Y equals, use your calculator, put in some stuff, or not some stuff, but basically the equation right there. Or just wait for me because, again, you don't think you need your calculator, which means I won't let you use it for the test. And we get $73,000 flat. Well, looking at those values, which job would you want to have I think I would choose again, which I think is what you're choosing, is the one that we're going to make the most money after 8 years. 88,000 is pretty good chunk and change to earn. So we want job A. Why? Because they do want us to justify our answer. Well, let's write some sense. I was going to actually draw it out, but let's just write out because I could probably do it a little bit better. And it'd be better to read too as well. So we want job A. Because, well, you make more money in job A. So because job A makes more money in 8 years than job B. And we can see it with the values. You can even put an inequality because 88,000 is greater than 73,000. So that can also work as well. All right. Now, this is the last one we're doing together. So number 3 is yours to do. We might do one more, but your number 3 is yours. So here's number 3. You're going to pause this video and try this one out, please. Pause the video now. Pause. So here you had worked a part-time job for 5 years, and there were 2 offers. One that pays $15,000 to start plus a raise of $400 a year, while the other pays $10,000 to start plus a raise of 7.2% a year. So we did our math. Of course, the $400 was our linear option since we're increasing by a value. That gave us $17,000 after 5 years. Our 7.2% option, which of course was our exponential option because it's a percentage, got us $14,157.09. Which option would you take? Well, of course, I want more money, duh. And so the $400 job option, because it pays more after 5 years. Oh yeah, $17,000, I'd rather have that than $14,000. An extra $3,000 can go a long way. All right, number 4. Again, this one is for you to do, so go ahead and pause this video and try this one out, please. Pause the video now. So, for number 4, we had 2 different cars depreciating in value, which means they were losing value. So hopefully you did the minus for the R value and the minus on the slope for the other car. We had the Toyota Camry that started at $27,000 and depreciated by 4.5%. So that was our exponential model right here. So we converted that percentage to a decimal, plugged it into our exponential model, and we got leftover $17,037.17. Our Nissan started at $27,000 and also depreciated, but this time by $1,500 a year. Of course, that is just a value, which means that was our linear model. So then our slope was negative 1,500 since we are depreciating. Our starting value, 27,000. And then, of course, plugging it all in, we ended up with $12,000 for our Nissan minivan. Well, which one retained? The key thing was here, retain the most value. By year 10, obviously, the Toyota is worth more still. All right, next one. Let's do this one together. You accept a job that pays out $25,000 a year for the first year. Well, that's pretty nice. You are given the option to either earn an additional, so earn, which means we're going to add an additional $550 each year, or we can have 5.2% of that current salary earning each year. You plan to stay on this job for 3 years. Which option do you choose? And be sure to explain. So of course, first, let's look at the first one they gave us, which is the option of earning $550 a year. And since it is a value, that means it's linear, which hopefully by now you have gotten a picture of that. What is your slope? Well, what are you increasing by? 550. And we are increasing because it does say earning. And then what's your starting out at? 25,000. And so what is our X value? We're looking at 3 years. So go ahead and plug that in. So it'll be 550 times 3 plus 25,000. Use our calculator to compute that math. And we get $26,650. That's not bad. $26,650. All right, now let's look at our other option. That was the 5.2% option. Since it is a percentage, that means it's exponential. So let's use that exponential model that we've been using quite a bit today. Again, what's my starting value? 25,000, the same as the other. What is my rate of change? It's 5.2%, but we need to divide it by 100 to make it the decimal to use, which is 0.052. There we go. And then, of course, our years is still also 3. Go ahead and plug these values in. And then, of course, remember we're adding, because remember we're earning, so we're adding our R value of 0.052 and then raising that whole thing to the third power. Again, plug this into your calculator to have it do that work for you. I mean, you're going to want to plug it in now, like I've been telling you, because if you don't, you might not be able to use this on a test, and man, this unit definitely needs one. So we get 29,106. And let's see, how many cents we got? 32 cents this time. Ooh, nice. So which one would you plan to choose? If you were at that job for 5 years, well, of course, you should choose the one that has more money. Well, why would you choose the 5.2% option? Well, we just said it, because it makes more money than the $550 option. So let's go ahead and, of course, write that in a complete sentence. So 5.2% option, because it makes more money in 3 years. Awesome possum. I do believe we have one left, and yes, we do. And guess what? You knew it. Yes, you did. This one's for you to do. So pause this video and try this one out, please. Pause the video now. Pause. Okay. So for number 6, you accepted a job that pays out $10,000 for your first year. You're given the option of earning an additional $390 each year, which was our linear model, which is the one on the left, which started at $10,000. $390 was each year for 5 years. We ended up with $11,950. Then you also could have chosen the 3.55% option, which of course is the exponential option because it's a percent. And we get, after we converted our decimal or percentage to a decimal and all that some stuff, plugged it all in, we get $11,905.58. So it's a tough choice between the two, but definitely I would go with the $390 option because it does make more money in 5 years. It might not seem as much more, but $44.42 can actually go a long way for something. That's at least 2 outs for the date night. So that's better than no date nights. All right. Thank you for participating today. You are amazing. Go ahead and do the Google slide problems if there's time. If not, take the quiz, please.